Hello, welcome to the video lecture of Computer Architecture and Organization. I am Priyanka, Assistant Professor in Computer Science and Engineering Department from Ajay Kumar Garg Engineering College. So this lecture will be talking about the control unit, and in the very first topics related to control unit are instruction types, then instruction formats, and instruction cycles and subcycles. Like we'll be discussing about that how the instruction is being divided further into the cycle and subcycles. So that's the agenda for this video. Okay, so first talking about instruction set architecture. So in this, the instruction set is actually the interface between the hardware and the software part, right? So we need to send some instructions, some commands from the hardware to the software. So that is being done with the help of instruction. So instruction is a very important entity for doing that task, and now it depends that what kind of instruction we are forwarding, right? So for that we have different categories of instruction. So we'll be talking about instruction formats. So format will be that what all data would be stored in that instruction, and then we'll be talking about various addressing formats. We have already read this in addressing modes that we could have the address in memory, we could have the address in registers, or we could have the address the data from the input output devices. So from where we are picking up the data, so depending on that thing, we have different addressing modes with us. Now with a particular type, like if I'm talking about register, so with register we could apply different operations. Similarly, we can apply various mathematical operator, logical operations. So different operations could be there being specified in the instruction set itself. The next is encoding in the instruction set. The instruction set is being encoded in the format which is being understandable by the computer. And now how the data is being stored in that instruction, that is also being specified. So the instruction is actually the abstract form of dealing with the hardware, with the software. So we'll be talking about that. Very first is instruction format. So what is an instruction format? What happened when we run a computer program? So we have a program which consists of multiple instructions. Now every instruction could be of any type, and that instruction is actually for a specific task, right? So we have suppose we want to read data from the input device, or we want to print something onto the device. So every instruction is doing a specific task. Now for that we need to store the content in that instruction. So we actually divide the instruction into three fields: mod field, operation code, and address field. So these three fields are the important part of the instruction, which tells that what kind of instruction that is, what kind of operation we are going to perform, and how we'll get that data on which we need to perform the operation. Alright, so first talking about operation code. So first talking about operation code, this specifies that what kind of operation we want to perform, whether we want to perform a logical, a mathematical, or reading or writing. So what kind of operation is being specified using this field. Mod field is just to tell that whether we are working with a register type instruction or input output or memory based. And in memory there could be a direct or indirect addressing. So we're going to talk about in detail about these fields. And the address of the operand on which we need to apply the operation is there in this address field. So these three important fields are there in case of an instruction. Alright, so let's talk about instruction formats. So it depends on a particular CPU organization, that what kind of organization that is. We could have three categories of different CPU organization. First category is single accumulator organization. This is actually a one address instruction. Now in this what happens is that we say that we have one thing in our accumulator, right? Suppose we want to perform addition operation. So I need two values, A and B, on which I need to apply the operation, and I want to store the result in another variable C. So basically I need 3 variables for just performing the addition and storing the result. But I can eliminate one by using C is equals to C plus B. So by this I need only 2 addresses. But here we are saying that if we are using one of the address in accumulator, so we don't need to specify the accumulator in our instruction. So if I would be replacing this C with accumulator, so now the instruction has just need one address, which is a B address. We don't need the address of the accumulator, as because accumulator is a part of the CPU, we don't need to specify. So this instruction, when I am writing add X, this actually means we want the content of X which is there in the memory, pick up that content, add it with the accumulator and store the result back to the accumulator. So this is a accumulator based instruction where one address is the accumulator and other we are specifying in the instruction. So this is accumulator based. Second category is we could take the use of registers. So in case of registers, we could have a 3 address or we could have a 2 address based instruction. So let's see how does it works. As I given you an example of that, we need to perform the operation, that means A is equals to B plus C. So here we need 3 addresses. Alright, so let's suppose that these values, these datas are being stored in registers R1, R2, R3. These are general purpose register. So suppose I have this, I have to add R2 plus R3 and store it in R1. So I can write it like add R1, R2 and R3. So by this, actually this could be meant as that the R1, R2 and R3, so this is being treated as that this is source and this could be a destination. Alright, or it could be treated as this is destination and these two are source address. Alright, so it could be, it depends that in which we are taking it as left to right or right to left. So we can take it like this. Suppose we are following it like that first address is the destination address. So we'll be adding these two and storing the result in R1. So here 3 addresses are there, 1 destination and 2 source addresses. Next instruction is saying that we are just going to use 2 addresses. So in this 2 addresses, we are not, one address is for source as well as destination. So here in R1, we are doing R1 plus R2 and storing the result back to R1. So R1 is working as source as well as destination. Alright, so this is 2 address. Now similarly, if I talk about move instruction, so move is just transferring the content of one register into another. So we need only 2 addresses. So the content of R2 is being transferred to R1 like this. Now if I talk about add R1X, so here R is the register and X is a memory location. So we can work with register as well as memory location. So the content of X is being added to R1 and being transferred to R1. So this with the help of registers, we can actually make an instruction of 2 address as well as 3 address. Now the next category is stack organization. So with stack organization, we don't need any address. With stack organization, we don't need any address. It's a 0 address organization, as because here just see an example, we are writing add. So add is from where the values will come. The values will come from the stack. So we'll see this in detail, that we'll fetch the top 2 values of the stack, we'll apply the add operation and store the result back to the stack. So here we don't need any address because the values are there in this stack. So when we are using stack, that instruction is called a 0 address. Now let's understand these with the help of an example in detail. So I have categorized the instruction into these 4 categories. We have 4 types of instruction format. 3 address, where the 3 operands are being specified as source, 2 source and 1 destination. Then 2 address is like 1 source as well as destination and the other operand is working just like a source. Then 1 address is that we are just using 1 operand here and the other operand is being taken from the accumulator. 0 address is that we are working on stack. Right, so we have seen this in the previous slide. Now let's just understand this with the help of this example. we have this expression A plus B into C plus D. Now we need to store this using 3 address, 2 address, 1 address and 0 address instruction. So if I talk about, we have A, B, C, D and X. These are the memory addresses, and let's see 3 address instruction. So here first is that we need to solve this. We need to solve this expression, and for this we need to first solve this A plus B, that's in bracket. So if I talk about 3 address, so I can specify 3 address at a time. So A would be the first, B would be the second, and I would be storing the result of this addition into a temporary register. So I am using add R1 A comma A and B. So the A and B is being added and being stored into R1 register. So first we have done this part. Now next part we need to consider this, that we need to add C and D and store the result in a register. Suppose I am taking R2. So the instruction would be add R2 C comma D. So the values of C and D are being added and stored in R2. Now I have the values in R1 and R2 registers. Now I need to perform the multiplication operator. So just apply multiplication X, R1 and R2. So the result is being stored in X. The values are being taken from R1 and R2. So using these 3 instructions only of 3 address type, we have solved this expression. We have done this expression. Now let's just do it using 2 address and 1 address. So in case of 2 address, we just have 2 addresses. So we will be treating one address as source and destination, and the other is as a source. So they again the same expression. So here we have this A plus B. Now for this A plus B, we can only use 2 address instruction. So what we can do is, let's just store this A in R1. So I have stored this in a register, and B is there in B itself. So then perform add R1 and B. So R1 and B will be added, and the content is being stored in R1 itself, as because in 2 address, the first address is destination as well. So the R1 is equals to R1 plus memory ka B. So the whole plus value is there in R1. Now let's just consider C and D, C plus D part. So for this we need to again move this to another register. So we have applied a move instruction. C, the content of C is being moved to R2. Then we need to apply the add operation. So add will add these 2 values and store the result back in R2. So add R2 and D. So R2 is having C and D. Those 2 are added and stored in R2. Now we have first in R1 and second in R2. Now R1 and R2, we need to apply the multiplication operation. Multiply R1 and R2. The result is being stored in R1 itself. And finally the result is in R1. Move that value to X. So just move that value to X. We got the final result in X itself. So this is how the 2 address works. Now let's just assume 1 address instruction. So in case of 1 address, we are considering that we have an accumulator with us. 1 value is there in the accumulator. So first what we'd be doing is, we need to solve this. So we need to store 1 out of these value in accumulator. So this value let's put that value in accumulator. For storing any value to accumulator, we have an operation called load A. So this load A will load this A value to accumulator. So the content of A is being transferred to accumulator. So this is an accumulator A, and the other value is in B. So we are just using add B. So add B is actually means adding the content of B with the accumulator and storing the result back to accumulator. So this content is there in accumulator. Now we need to move to the second part, but again we need to take use of accumulator. So we need to first remove this value from the accumulator to any other temporary location. So what we are doing is store T. So this store T will take out the value from the accumulator and store it in T. So the content of this is being transferred to T now. Alright, now moving on to this part, then again store the C value to accumulator and D is there. So just apply add D. So this add D will add the content of D to the accumulator and store the result back in accumulator. Now we have this complete value in accumulator and this in T. So just apply that we need to multiply T. So multiply T will multiply the value of T with the accumulator and store the result back to the accumulator. So finally we have the result in accumulator and we need to store it to X memory location. So just use store X. So by this X will be having the value which is there in accumulator, the final result. So by this one address we need to take use of accumulator. Okay, moving on to 0 address. So in 0 address we need to take use of the stack. So first we need a stack. So if I talk about stack is just like one end closed. So this is like a container which is having only one end open, which is used for inserting as well as taking out the values. Alright, so this stack follows the concept of FIFO, first in, first out. That means the value which is being inserted first is being taken out first. Sorry, it's LIFO, last in, first out. The value which is being inserted at the end would be taken out first. So here we are having a pointer which is called TOS, top of stack, which is if the stack is empty, it is pointing to -1. That means there is nothing in the stack. Okay, now we need to store this expression into stack and need to solve this, right? But before doing that, stack does not work on infix expression. This is an infix expression. We need to convert this to a postfix expression. So just converting this, we'll get AB plus. By this, we'll get CD plus and multiplication will move to the end. So finally, this is the expression. So just consider this expression, take one value and store it in the stack. So initially, first we have taken A. So A is being stored in the stack. Then next is B. So B will be stored in the stack. At this point of time, the TOS is pointing to B. Now next is plus. So when an operator comes here in the stack, so just see first we have pushed two values. So with stack there are two operations, push and pop. Push is to push a value, pop is to take out a value. So we have pushed A and B and now we have to apply add. So what add will do, I am not specifying here any argument, any operand, as because add will work on the last two arguments of the stack. Just take out those values, apply the operation, store the result back to the stack. So what it will do, it will just take out these two values, just add this plus operand on A plus B and store it back onto the stack. So till this point we got this and this is the top of the stack. Next is we need to insert C. We have inserted, now top of stack is pointing to C. Then again next instruction is push D. So just push D here. So we have this in our stack. This is pointing, top of stack is pointing to D. Now we need to add. We have a plus operator here. So add, when I add here, so this will pick up the last two values, just apply the sum. So we'll got here A plus B was already there and it will just add C plus D. So we have these two values in the stack, right? Now we have another operator, multiply. So just apply multiplication. So when we have multiplication here, so this will take out the last two values of the stack and the final result will be A plus B multiplication C plus D. So by this we have the final resultant in top of the stack. So this is the top of the stack at this point. Now this is the final result. Just take out that value and store it in X location. So we got it. So this is how the stack works, where we are just using two operations, push and pop of the stack, and for other operations we are not specifying any operand, we are just taking out the values of the stack, applying the operation and storing the result back to the stack. So this is how it works. Next, instruction code. So just to understand the different instruction codes, let us first assume that suppose we have a computer which is having a configuration of this 4096 cross 16. So this says that we have these many addresses of this much size, right? So every field is of 16 bits. So that means we are saying that this size is 16. So that means our data is of 16 bits. Now talking about that, we have 4096 addresses. Now to get 4096 addresses, we just calculate 2 raised to the power, it comes out to be 12. So we need 12 different bits to identify any of the location of this 4096 memory space. That means I am saying that we have, this is address 0 and this is address 4095. This is our total memory space. Alright. So just to refer to any address, we need 12 bits to refer to that. So for the rest of this lecture, we will be taking these two consideration, that the address is of 12 bits just to access 4096 memory spaces, and every address is of 16 bits. Now this memory would be storing the data as well as instructions. So just see here, we have instructions as well as data in the memory, and everything is of 16 bits, right? So this is the assumption. Now let's just see instruction code formats and instruction cycles. So first is we have different types of formats. So I have told you that these are the 3 different fields of instruction code format. We have 3 things here. One thing is the mod field, then we have opcode field, and then we have address field. Now this by these 3 fields, we need to decide that whether the instruction is of memory type, register, or input output. So just see here, we have 3 categories of instruction: memory based, register based, and input output based. So if the memory based, that means the address is there in the memory. Register means the operand's data is there in the register, and input output means we are either taking the input of any data or we are just giving the output to any of the data. So how the instruction will specify that this is which type of instruction? So we need to take that decision using this opcode field. Now we say that we have designed the instruction in such a way that if the value, the 16-bit instruction, we have just talked about that the instruction is of 16-bit. So 16-bit is being divided into 3 parts, like the I bit is just of 1 bit, the opcode field is of 3 bits, and the address field is of 12 bits. So 12-bit address, 3-bit opcode, and 1 bit for a mod field. Now we will be considering this opcode to find out whether the instruction is of memory, register, or input output. Now if the value of opcode is from 000 to 110. Now these are the 3 bits are there, so the value could be 000, 001, 000, 010, 011, 100, 101, 110, and 111. So this is actually binary decimal number 7, this is 0. So just see, we are just saying that only this 1117 is used for either register or input output. The rest of these 6 is for memory type. Alright, so if the value of opcode is from 000 to 110, so it is a register type instruction. Oh, sorry, memory type instruction. But if it is of 111, so the instruction could be of register type or it could be of input output based instruction. Right, so this is the first categorization, that how we will decide on the basis of opcode 3 bits, we can decide whether the instruction is memory based or register output or input output. So if it is 111, it is register or input output. Now if it is a register or input output based, how we can identify? Using this I bit. If the value of I bit is 0, it is a type of register based. If the value is 1, it is an input output instruction. So clearly it means that if your first 4 bits are like this, 0, 111, so it is a register reference based instruction. if your first 4 bits are like this, so it is your input output based instruction. So clear cut, we can see and we can analyze that with which kind of instruction is this. And for the rest of the first 4 bits, the instruction would be of memory based. Now in case of memory based, we say that except these we have memory based. Now what about this I field? This I bit value is either 0 or 1. So 0 says the address is a direct address. 1 says it's an indirect address. So this I bit will decide either it is a direct address or an indirect addressing mode. Now let's just understand how direct and indirect works. So for that, let us suppose that we have this instruction with us. This is 0 bit. 0 bit is specifying that it is a direct address. Here 1 bit is 1 value is specifying it is an indirect address. So if it is a direct address, we have the address here, and on this address you will get a value. So just move to that address, you will get an operand and just apply the operation and you are done with it, right? Now in case of 1, it says that on this address you are not going to get a value, you will get an address. So just move to this address, you are getting another address. Now move to that address, you will get the value. Alright, so directly means that the address of the operand is specified in the instruction directly, and the address is specified indirectly using, and we specify it using the I bit. 0 is direct, 1 is indirect. Okay. Now next, instruction cycle. So as I've told you that the complete program is being divided into instructions, and every instruction is actually working in an instruction cycle. So there is a complete instruction cycle for every instruction, and every instruction cycle is being divided into sub-cycles. So we have divided the task of an instruction into multiple tasks. So these are the 4 following phases or following sub-cycles of an instruction cycle. First phase is that when we are talking about that we need to execute an instruction. So we need an instruction. So we need to fetch that instruction from memory. Second part is we will be decoding that instruction to understand that what kind of instruction that is, and what are the bit value, mod value, what is the operation, and from where we'll get the address. So we'll decode it and understand the instruction. Then in the next step we are going to read out the effective addresses from where we'll get the operand, and finally we'll execute the instruction. So every instruction will undergo these phases, and when we are done with it, we'll stop at the end of the program. So let's just first understand the first and second step, fetch and decode step. So fetch and decode step says that we need to fetch the instruction from the memory. So from where we'll get the address of the instruction which needs to be executed. So we have read that we have a special purpose register which is called PC, program counter. Program counter is containing the address of the next instruction to be executed. So we need to execute the instruction whose address is being specified in PC. So just take the content from PC. Alright, we need to get the address from there. And when we are working with an instruction, every time we will be clearing out the sequence counter to 0, which actually specifies the timing signal to T0. That means this is just the start of this instruction. And with every clock cycle, the SC is being incremented by 1, and this will move on like T0, T1, T2, T3, T4, so on, till the time the instruction is not complete. Alright, so let's just understand these 3 time signals. This is for fetch and decode. These 2 steps are for fetch and this is for decode. So what happened in a fetch case? In case of fetch, we have the address there in the program counter which we need to execute. So just take that content from the program counter, store it in AR. So address register is the one responsible for storing the address of instruction or data. So we are storing the address of that instruction which needs to be executed in AR. So that is our first step at time T0. Then at T1, we are taking the content of that memory, that memory address, and storing that in IR. So IR, that address, that the instruction from that address is fetched and being stored in IR. So we have the complete instruction in IR now. Now we are working on PC. So next instruction we need to, at the next time cycle, we need to execute on next instruction. So we are just incrementing the PC to PC plus 1. So that will move to the next instruction, so that next time we will get the next instruction address from PC. So by these two steps, we are done with the fetch. We have fetched the instruction from the memory, and that's there in our IR. So the result of this is there in IR. Now next step is that we need to decode it. So for decoding it, IR, we need to decode this. So we need to decode it and divide them into 3 parts as discussed earlier. So just see, the 15th bit of IR is for the mod bit. So just store that in I. So that is the mod field. Then from 0 to 11 bits is for the address. So store that in AR. So I is the 15th bit, AR is from 0 to 11 bit. Now we are left with 12 to 14 bits. As I've told you that these 12 to 14 bits would be having values from 000 to 111. So this 000 means D0 and 111 means D7. So D0 say D7 would be, values would be there. So just decode the values from 12 to 14 and store that in D0 say D7. If the value of D is D5, so that means the 12 to 14 bit are 101. So that is a 5 value. So at the end of this decode phase, we knew 3 things. What is the value of decode bit, what is the AR value, and what is the I value. Now let's just see the next, that talking about these two, how does that actually happens in the internal organization. So we have already knew this thing, that we have a bus with us for transferring the content. So just see, this is the bus. All this register memory are being joined together using this common bus. This is a common bus connecting all these devices. So suppose the first fetch phase was saying that we have the content in PC and we need to store that to AR. So to do this operation, we need to get the content of the PC and load it onto the bus. For that, we need to enable this. For enabling this, we need to do this values S2, S1 and S0 to be 2, as because PC is being connected at 2. So the value of S2, S1 and S0 will be 0, 1, 0. So this says that a value is 2. So this 2 value is actually selecting this PC, and the content of the PC is being loaded onto the bus. Now the PC content is there on the bus, and from the bus we need to load it to AR. For doing that, we need to enable this load operation of this AR, which will move the content that is there on the bus to AR. So this is how actually the data of PC is being loaded into AR. Now let's next just see the next phase. Next statement was that at T1 we need to take the content of this memory AR and store it in IR, and PC is equals to PC plus 1. So again, let's just consider this with the help of this diagram, that what we need to do is, we have the content in AR, and from this address of memory we need to read and store it on IR. So this is what we need to do. So we need to read the content of the memory. So this is where the memory is, and this is the value. So to select memory, the values on select lines would be 111. So this 111 will select this memory, and the content from this address will be read out and stored onto the bus. So now the content is there on the bus. So this is on the bus. Now to store the content from the bus to IR, we need, this is the IR, we need to enable this load. So that will transfer the content of bus to IR. So this is how first we are selecting memory, the content of memory is being transferred onto the bus, and by load enable the value is being transferred to IR. So we got this. Next operation at this cycle is that we need to increment PC by 1. For doing that, this is PC INR operation. This is increment PC. So by this, enabling this operation, this will increment the value of PC by 1. So this is how does it works. So this is the internal organization, that how the content are being transferred over to the bus and registers. Now next. Now just understand this flow chart of instruction cycle. So we are saying that this is the complete flow chart. Initially we have started with SC is equals to 0. The sequence counter is 0. Then at T0 time period, we have transferred the content of PC to AR. That is the first fetch phase. And at the second, we have taken the content of AR and transferred it to IR, and PC is incremented by 1. So these two steps I have already explained. This is a fetch phase, and this is a decode phase. So in this decode, we are just doing 15th bit, transferring 15th bit to I, and 0 to 11 bits to AR, and decode 12 to 14 bits. Right. So by this we got it what is the opcode value. Now the opcode value could be from D0 till D7. So now we need to check if the value of D7 is, if the value is D7 or not. That means if it is D7, that means if it is 1, that means it's a D7. If it is 0, means that it is not a D7. So if it is a D7, so that says the instruction is either a input output or it is a register based. It's not going to be a memory based. Alright, so D7, on the basis of D7, we have taken this decision whether the instruction is memory based or not. So it's not a memory based, it's a register or input output. Now we need to check this I bit. If the I bit value is 1, so that means it's an input output. If the value of I bit is 0, it is a register based instruction. So if it is 1, we will execute the input output. If it is 0, we will execute the register based instruction. Now if the value of D7 is 0, that means it's a memory based. In case of memory based instruction, we could have a direct address or an indirect address. So we will check out the I value. If I is 1, it's an indirect address. If I is 0, it's a direct address. When I is 0, so at T3, we don't need to do anything. We have the address with us and we will execute the memory based instruction. But if the value of I bit is 1, so that means we have this address with the, we have indirect address. So we will take out that address from the memory, and that is the effective address, and then we will execute the instruction. Now when we are done with the instruction, at the end of every phase, we are just moving the instruction to the next cycle. So this is how the instruction cycle works. So we say that D7-I T3, that means we have D7 dash, that means we are talking about these two are memory based. So we have memory based instruction, and this is our indirect and this is direct. So D7-I T3 is a clause of indirect instruction. D7-I T3 is a direct instruction, and if it is D7I T3, so that means it's a register reference. D7I T3, that means it's an input output instruction. Thank you. That's it for this lecture.